11.6 Volumes with cross-sections 1, squares, and rectangles. We know that the volume of a rectangular prism, or a rectangular solid like a cube, is length times width times height. But why? Well, in this figure we see that if we have a 4 by 4 by 4 cube, we can look at this cube as having 4 squares from top to bottom, 4 rows. Each row is 4 by 4. So each square has an area of 16. So the volume will be 16 times our height, which is 16 times 4. Now, in other words, the volume of a rectangular prism is really just the area of the base times the height. Okay. In calculus, we're going to be integrating from left to right. This one, when we're doing dx. This is really dy. If we do dx, we're just effectively rotating 90 degrees counterclockwise. So this is what we're really doing. So the volume of the rectangular prism will be the area of each base, each slice. So each base is really each slice times our width. That means that the volume of our cube, well, the area of each slice is just the side length squared. That's the area of the base times our width. And if we have a rectangle, then the area of each slice is going to be side length times our height. That's the area of the base times our width. Okay. Now we are ready to find volumes of solids in which cross-sections are areas between curves, which is the area is what we've been learning in the last 2 lessons, 11.4, 11.5. Example 1. Let R be the region enclosed. Enclosed means bounded by f of x equals square root of x, and g of x equals x squared. So here we have square root of x, which is f of x, and g of x, which is x squared. We see that there's a region R here. R is also the base of a solid with square cross-sections perpendicular to the x-axis. What does that mean? Well, here's a nice simulation created by Michael Andrzejkovic. Thank you to that person. The cross-section is, if our base is this area, R, we see that the base is right here. The cross-section, well, this square is an example of a cross-section. So here we see that we have a bunch of cross-sections where the base is just formed by R. The cross-section is perpendicular to our x-axis and also y-axis, really. Okay. And we see that as f of x minus g of x increases, the cross-section is getting larger and larger because the side length is getting larger and larger. And as f of x minus g of x decreases, the cross-section gets smaller and smaller. And these are always squares. Okay. Well, when we do that, and we add up all the cross-sections, we get a solid that looks like this. We are trying to find the volume of the solid. The solid is the sum of the areas of all of these cross-sections. They're all squares. So here's our solid, and we're adding up a bunch of different cross-sections. Okay. Well, the volume of the solid, as we saw earlier, is a cube, so it's side length square times width. So it's side length squared times width. The width we're integrating from 0 to 1. Okay. So a is equal to 0, b is equal to 1 really for this one. We're integrating from 0 to 1. And the width is going to be dx. because we're integrating. So dx is right here. So just like our last lesson, dx, here's a very, very narrow strip, except that this is really the base of a solid, the base of a square. And the square sticks out like this. So we have a square sticking out like that. Well, what is this? Let's use a different color. What is this? This has to be f of x minus g of x. So the side and the height is also a square, so the height is the same. It's also f of x minus g of x. So the side length is f of x over g of x, and the volume is going to be f of x minus g of x, the whole thing squared, times dx, and we integrate it from 0 to 1. A is 0 and b is 1 for this problem. So this has to equal f of x is square root of x minus x squared, and we take the whole thing and we square it. Okay. So when we do that, this is really just equal to this thing. The integral from 0 to 1 of square root of x minus x squared, and the whole thing squared dx. We can go to Wolfram alpha to help us solve this integral. We are trying to integrate square root of x minus x squared from x equals 0 to x equals 1. When we integrate this, we get 1/3. So this is equal to 1/3. Alright, let's be careful here. I made a mistake when I typed into Wolfram alpha. It's the square root of x minus x squared, and the whole thing squared, because that's just the base. Whole thing squared from x equals 0 to x equals 1. And when we do that, we get 9 over 70. And we get 9 over 70. So that's the volume of the solid. That's the volume of this solid. Example 2. This time our volume is a cross section. So let S be the region bounded by f of x is equal to x squared minus 1, g of x is equal to x minus 1, and x equals 3. So here's our region. We see that x squared minus 1 is bigger than x minus 1. And they intersect at x equals 0. And they intersect at x equals 0 and x equals 1. And what matters here is x equals 1. That's where the point where that's the left-handmost intersection. And on the right-hand side, x equals 3. That's where the bound is. So we're going to be integrating from 1 to 3. S is the base of a solid. Each cross-section is a rectangle perpendicular to the x-axis with a height of 3x. So given any of these lines, our cross-section is a rectangle that looks like this. Write, but do not evaluate, an integral expression that gives the volume of the solid. So here, all we have to do is write the integral. We don't have to calculate. This sometimes shows up on the AP test, and it's very common in college classes in math and science, because really what they care about is that they know you can use a calculator to calculate the integral. They want to know if you know how to set up the integral. So all we have to do is write an integral, and then we're done. So we know that the volume of our rectangular solid has to be the area of the base times our width, because we're integrating from left to right. Okay. Now, the thing is, the width is just dx. The area of the base. Well, the area of the base is our length, which is side length, times our height. We're told that our height is 3x. So height is replaced by 3x. Okay. So really, this is equal to our integral from a to b. And we saw earlier that a must be equal to 1 and b must be equal to 3. So side length times height dx is really just equal to side length is really just f of x minus g of x. And height is really just equal to 3x. That came from the problem. Height equals 3x. Okay. So the volume is really just the integral from we're integrating from 1 to 3 of x squared minus 1 minus x minus 1. Make sure to put the parentheses around x minus 1. That's the side length times our height, which is 3x, times our width, which is dx. This is actually finished, but if you want, we can simplify even further because the negative ones cancel. These two cancel. So we end up with the integral. The volume has to be the integral of 1 to 3 of x squared minus x times 3x dx. And that's the volume. We could simplify this even further or even calculate it, but this is good enough. All right. So what did we learn? We learned that the volume of square cross sections is just the side length squared times our width, which is dx, as we integrate from a to b. The volume of rectangular cross sections with height h of x, the height can be any function, doesn't have to be a constant, h of x, is going to be the integral from a to b of side length times our height, h of x, times our width, dx. Okay. That's it for this video.